First off, I've input these test scores as they are into the grade book. So if you want to see exactly where you are with this in there, that's available. Now, if you want to, and you don't have to if you don't, just an option. But again, you can correct your test for 25%, okay? So if that will benefit you, you can do that. If you're pretty solid in like the A, B range, then hey, probably not worth the effort, okay? But if you want to, that's an option. So you can see exactly what your grade is right now with this test score figured in, okay? So again, like let's say for example, you miss number 11, which was a common one that was missed. So, and let's talk about number 11. So here's the deal. So on number 11, here's your setup, okay? And you have an electric field of 1200 directed to the right. So this is the direction of your electric field, right? And it has a value of 12,000 newtons per coulomb. So you have the distance between them, an electron is projected from plate A, okay? So this is an electron. So a lot of you did it right. And you started off and you said, oh, okay, well, we can find the force using EC, okay? You know the value of the field, okay? 12,000. You know it's an electron. You know the charge. So you can find the value of the force. And then you said, oh, okay, well, Mr. Verkamp, you taught us the force equals mass times acceleration. We might have mentioned that once or twice, okay? And you found the acceleration. And that's 2.11 times 10 to the 15th meters per second squared. And that's cool. You got that. Now, this is where the wheels fell off, right? So what you have to decide is if this is an electron, and that's the direction of the electric field, okay? So if this is the direction of the electric field, the only way that becomes that's the direction of the electric field is if plate A has a positive charge and plate B has a negative charge. Okay, that's the only way it works. So leave the electron out. If this is the direction of your electric field, you know that has to be your positively charged plate, because if you put a positive test charge here, a positive test charge here, it's going to be pushed in that direction. That's the direction of the electric field, okay? So if you put a proton in here, that proton is going to get pushed in that direction because that's the positively charged plate. And if you put a proton in there, it's going to speed up. But you don't. You put an electron in there. So what's the electron going to do is it gets shot across there.
Slow down.
It's going to slow down. So if you're shooting this thing at 2.0 times 10 to the 7th meters per second, okay, and you realize that it's an electron, you know your final velocity on the other side has to be less than what you started. So since it's going to be slowing down, you can eliminate D and E, okay? Can't be either one of those answers, but those are the answers that a lot of you had, okay? So look at this in terms of V squared equals V naught squared plus 2AD. And you all did this, right? But here's the deal. You have to make that acceleration a negative value, okay? That's the only way that way you subtract that value from that V naught squared. That's how you get a velocity that's smaller. And what the vast majority of you did that missed that question, you just took that number and you blissfully plugged it into that equation without realizing, oh, that's not going to end well because that thing has to slow down, okay? And you plug that in and you violated every law of physics because it's going to be slowing down, okay? So that it's like you knew how to do it, but yet
No, not that I.
Kind of the wheels fell off on that one.
So what were you supposed to do then?
So, thank you. Just throw that up in the tray. So that was missed a lot. The other one that was on number 14. So here's the deal. So on number 14, you've got, here's A, and that's negative Q. And then here's B, and that's positive 2Q. And there's 2, and there's 3, and there's negative 4Q. Okay? And it says, which of the following ranks the magnitude of the net electric force F on each point charge due to the other charges? Okay, so this is fairly complex problem because you have to figure out, okay, hey, what's going to happen here? So if you look at this in terms of, because of the fact that you're talking about that net electric force, right? So since you're talking about force, that's going to be K Q1 Q2 over distance squared, right? So again, if you look at just this in terms of the fact that it's distance squared, so what you have to figure out is sit here and go, okay, well, come back here. So here's force C. So what you got to do is figure out, okay, so here's force B. So what's it going to feel? Okay, so if you just start with this idea, so just leave, you're just talking about the force that it's going to feel from the other two. Oh, well, that's going to be K times Q times 2Q divided by like 1 squared. So that's, and don't even worry about the K because that's just going to be a common factor. Oh, so that's 2Q squared. Now, from this side, you're going to have 2Q times 4Q, but then that distance is going to be 2 units, but that's going to get squared. So that's going to cancel out the 4, so that's also going to be the same. So those two values are the same, so that's in effect going to create a net force of 0 because it's going to be pushed by one, it's going to be pulled by the other. So that's what you've got to do. You just kind of have to work each force through and say, okay, hey, start with A. What's it going to feel relative to B? What's it going to feel relative to C? And then do the same thing with the other ones. Start with C, what's it going to feel for B? And that's just what you have to do. Anyway, so that those two were the ones that were missed a lot. Then on 23 went okay. It was basically a lemming problem on steroids. So you had to go through and figure out how long it took to traverse this. And that's why I said what happens in the X stays in the X, what happens in the Y stays in the Y. So if you look at what's happening here, you can go, oh, distance equals velocity times time. I can do that horizontally because there's no horizontal forces to cause an acceleration. You get a very, very small amount of time, like 1.67 times 10 to the negative 9th seconds. So that's how long it takes to go through there. And then you can go, okay, well, we can find the force using Eq, and then we can divide that by the mass, and we can get the acceleration, and then you're just going to go distance equals 1/2 at squared plus v naught time. But vertically, there is no initial velocity, so that thing drops out. So basically, you're going to take that, plug that in there, find that acceleration, and you're off to the races. And I wanted the answer in millimeters. I didn't take off points, but it was like, oh, for the love of God, read it. And some of you got answers like bigger than the gap itself. Like, I thought that was kind of cool. On 24 was the one I was worried about. Okay, that was the one, that whole thing kind of gave me pause. So here's the deal. So you got a 15 nanocoulomb charge here, and then you've got an electron over here, and it wants to feel no net electric force. So you know it's going to be pulled in this direction. So that Coulombic force is going to pull it in this direction. So the only way you can balance that out is if the force from the electric field is going to push it back in this direction, okay? But because it's an electron, okay, then it's kind of, you kind of have to, in your mind, you have to kind of have to flip it through. So if the field, if this was a positive charge, right, and the field was going from left to right, it would push it. But since it's a negative charge, that field goes from left to right, then it's going to move in that opposite direction. So, and I was somewhat lenient on how I interpreted some of your answers, because I specifically said, is it going to move left to right or right to left? And some of you just said left or right. It's like, what does that even mean? Okay? So that's why I wanted you to specifically state moving to the left to the right or the right to the left. So because of the fact that this is an electron, and it's somewhat counterintuitive, because you would think, well, it's being attracted that way, that field should point in the opposite direction. Okay, but it's an electric field based upon a positive test charge. So that electric field is still going to be going in that direction, but that electric field is going to make it go, get pulled back this way to balance out that attractive force towards that. So anyway, let me see. On 28, and that was that one where you had to find the Coulombic charge on the sphere. So basically, it was a trig problem, basically. So you know the mass, so that upward force has to be 0.01 newtons to balance out the gravitational force holding it down. And you know that this is like a 10-degree angle. So your electric force is going to be this side. So the vertical component of this triangle has to balance out that gravitational force. So that's 0.01. You need to find the side opposite. So it's the tangent of 10 degrees, because that's opposite over adjacent. So it's just the tangent of 10 degrees times 0.01. That gets you the electrical force. Set that equal to Q1, Q2 over B squared, solve for Q. Okay. The rest of the test was pretty good. So, Evan.
Could you explain 29?
Which one?
29.
Okay. Is that with the molecule?
Yeah, I got part A.
Okay. So it's the easiest way to visualize this is almost like a spring. So you've got this electric field coming across here like this. And you have a negative and you have a positive value here, right? So because these are going to be random, right? So if you look on A, and pretty much everybody got A right. Okay, in the field, okay, like the field exerts a torque on them. So as this field comes in, it's going to push or pull, and it's going to make those things line. So those are those calculations that we did, okay? So we can calculate that value. But then the wild card then came when you get to C, because if you read C, it says, since the molecules enter the field line parallel to the direction like the molecules in the middle, the field exerts forces in opposite directions of the two atoms, the structures of the molecular bonds that give the molecules internal energy. So if here, let's say that you can kind of visualize this as being like a spring, okay? So imagine that let's say this is the negative end of the molecule, and let's say this is the positive end of it, okay? So since that electric field is going in this direction, okay? So here's your electric field. Let's say, let's just pick a point. Let's say this is the negative end of the molecule. and that's the positive end. So as this thing is going through, that positive end of that molecule is going to want to go in that direction because of that field. The negative end of the molecule is like it's going to get stretched. Okay, so anytime you make molecule stretch, it's like taking a spring, and when you stretch that, if you stretch that spring, that's going to increase that internal energy of the system. So one end is going to get pushed, the other one is going to get pulled. That's going to sit there, but there's a limit on how far you can do that. So it's just that it's like a spring oscillating back and forth. And because you have opposite ends being pulled in that electric field, it's going to stretch. And anytime you make atoms move or vibrate, that's what creates thermal energy. Okay? Does that make sense? Okay. Anything else? Okay, so if you want to do the corrections, the sooner you can get those in, the better, because that way I can have time to get those input into the grade book. Got it? Good? Grand? Okay. So here's how these last 2 days are going to play out. So today we've got to go start talking about EPI, electrical potential energy. You're not going to have it, it's technically like chapter 21. We're not going to have like a separate test over chapter 21. We're going to get through the main ideas because normally on the AP test it isn't stressed that much. Speaking of the AP test, so I kind of know how to handle some things. How many of you, I know Patrick said you're planning on taking the AP test. Is anyone else going to take the AP test? Just you.
Oh.
You are. Okay. Anyone else can take the AP test? Now.
Paige might have.
Huh?
I think Paige might have. I don't.
Okay. Well, so let me give you some words of advice. Okay. If you're, maybe you are, maybe you aren't. So here's the deal. It won't. If you know in your heart of hearts, you know you're going into engineering. This will not count as your physics for engineering because it's not calculus based, okay? It won't count. The reality of it is that 95% or higher, depending on what study you look at, of incoming freshmen change their majors, okay? And so if you're thinking about whether or not to take the test is, I think it was like, what, 90, 95 bucks, I'm not sure how much it is, okay? So basically it's a $100 roll of the dice. So, like I said, because I look at the kids that have gone through here, oh, I'm going to dental school, like the kid who's dead set on going to dental school. He just graduated with a degree in accounting. I had another gal who was dead set, she was going to get a degree in microbiology. Okay, that was her thing. Got all the way through basically her junior year. Just on Facebook announced that she's changing her major to graphic design. Okay? So the reality of it is that most people just don't change from like mechanical engineering into civil engineering or something like that. Like they completely change their major. I mean, it's like, wow, this isn't really what I wanted to do. So, and it's a very niche field that actually needs calculus-based physics. So if you're going into medical school, veterinary school, business, something like that, you don't need the calculus-based physics. You only just need physics. And I know some of you are taking it for dual credit through W8 credit. Here's my point, is that most of the time the kids take the AP test, usually score high enough to get credit. Okay? Not always, but for the most part they do. So if you're thinking about it, it's like, oh, do I take the test or not? Don't know. Okay? It's basically a $94 roll of the dice, of whatever it costs. But again, if you have to take the same class, KU, WSU, K-State, whatever, okay? To get this class, you're talking about basically $350 a credit hour. You're gonna probably pay $200 for a book that you can't sell back. And now you're talking like $1,400. So it's kind of a roll of the dice. You can sit there and go, okay, hey, maybe I'm out $94. If I need it, great. If I don't, hey, I'm out $94. But then you go, wow, I could have taken that test and gotten out of four or five, I don't know which college you go to, 4 or 5 credit hours of college, that now I'm gonna have to pay a huge sum of money to take, okay? So, that's just a word of advice, because in my time, I've known more kids that don't end up in the major that they start off with. And, you know, these caliber of kids like you, now some do, like, you know, Christian's brother, John Cole. I mean, I knew John was not going to change his major. Okay, if you know John at all, it's like I knew he was not, it was set, stamped. But I'm just telling you, a lot of people change their major. So I'm going to send the information out to everybody. You have until Friday to like 3 o'clock or something like that to decide. Okay, so I'm going to send you that information. You have to go to the College Board website. You have to create an account, and you need like a join code. I will send that out. Okay, but it's just something to think about. Evan.
And if you're taking it for dual credit, that's like the same as the AP does, right?
Yes. The one advantage that the AP gives over dual credit is that the AP credit is more transferable if you're going out of state, okay? Like if you're going to school in Missouri, Oklahoma, Nebraska, something like that, okay? In school, if you're within the state of Kansas, you're good, okay? Where you can potentially get trouble is outside. That's the advantage of the AP because it's more universally recognized than classes through WSU Tech. But if you know you're staying within the state of Kansas, you're good. Okay? All right. So let's talk UWI. So if you look at the types of energy that we've dealt with so far, this is actually kind of a nice summary to get ready for the test, your midterm on Friday. So what are the 2 general broad classifications of energy? Yeah. So on your energy thought process, you can generally have kinetic and you can have potential. If I can spell. Okay? Now, broad ideas. Cassidy, what are the 2 types of kinetic energy?
Oh boy. One is rotational
Rotational
and translational.
and translational. Well done. So for the added bonus, do you remember the equations for either one of them?
1/2 mv squared.
1/2 mv squared. Nice.
And then like 1/2 that little w thing squared, right?
1/2 I
W, whatever.
omega squared, right? So if you look at these both have the same idea. So if you look at yonder bicycle wheel, so if I just take this and I throw it, right? That's just going to be 1/2 mv squared. Here's the mass, the velocity, you double the velocity, you quadruple the amount of kinetic energy, hey, you're off to the races. So this is mass, which is the measure of inertia, times how fast you're going squared. Now, what does I stand for here? Moment of inertia. What are the 2 factors, count them 2, what are the 2 factors that affect moment of inertia? Radius and mass. Because remember, the general broad classification of moment of inertia is that it is mr squared. Okay? Now, do not memorize the moments of the equations for all moment of inertia going into the midterm final. If you need a specific equation for moment of inertia, like a thin hoop, whatever it is, I will give that to you. Okay? But what you need to remember at a moment of inertia is that you have 2 things that affect moment of inertia, mass and radius. You only have one thing that affects inertia, and that's mass. Okay? So you can have 2 objects of unequal mass have the same moment of inertia depending upon how you distribute the mass. So this is how fast it's going to spin. So if I spin pretty slowly, it has a certain amount of rotational kinetic energy. or make it spin faster, it has a much greater amount of energy. In both units, what are the units gonna be measured in? Joules, right? And what's another way to express joules? Newton meters. Okay, that's kind of cool. You guys haven't forgotten everything that we learned about energy, right? Now, let's say that I want to make this wheel spin. Did I just do work?
Yes.
Yes. And what's the broad idea of work?
Force times distance.
One option is that work equals force times distance. The other one is that it's some type of change in energy, okay? And that change in energy could be a change in rotational kinetic energy. It could be a change in translational kinetic energy. I could lift it up and I could change gravitational potential energy, okay? So no matter what, the broad idea of work is that it can be some force through some distance, or the broader idea is that work is going to be is changed in some type of energy. Okay, so keep that in mind when we deal with OOI. Okay. Now, can work be positive and negative, or can work only be a positive value? What did you say, Patrick? Wow, what did you say?
Positive or negative.
It can be positive or negative, okay? Because remember, your force is in the direction of motion. So if I like lift this up, okay, I'm doing positive work because I'm increasing the potential energy, right? Now, the gravitational force is acting downward. So if I lift it up, the work done against gravity would be a negative value because the gravitational force is acting down, but I'm lifting it up. But the work that I would do would be a positive value because this thing is getting lifted up. If I lower it down, I'm going to do negative work, but the work done in terms of gravity would be a positive value because that's the direction of the gravitational force. So work can be positive or negative, especially when you look at a change in kinetic energy. So if I take this at rest and I make it speed up, oh, my final rotational kinetic energy is bigger than my initial rotational kinetic energy. Oh, I did positive work. If I slow it down, I'm going to do negative work because I'm decreasing the amount of energy. Could rotational or translational energy ever be a negative value?
No.
Brady,
No.
why not?
That's the question.
Huh? Your answer is right. Well, why is it impossible for my rotational or translational kinetic energies to be a negative value?
Math-wise, you square the distance.
It's squared and it doesn't have a distance.
Yeah, okay. Mass, moment of inertia, those are positive values. So even if I did have negative velocity, what's going to happen?
It's squared.
It's going to get squared, okay? So rotational, translational, only positive values. It's cool with that. Now, let's talk potential energy. All right, so what's one type of potential energy that you could have?
Gravitational.
You could have UG, right? MGH. Got a tennis ball, lift it up, I do work, I store a certain amount of potential energy. If I take Hank and I lift Hank up, do I store the same amount of potential energy? No, I store a lot more potential energy. Why?
Greater mass.
Hank has a lot more mass, okay? So if I lift something up, hey, I get farther from the earth, I increase the amount of UG, okay? Pretty simple idea. What else could you have? We could talk about us, right? Which is 1/2 kx squared. So this is energy stored in a spring, and this is gravitational potential energy, right? Cool. Now we need to talk about OOI, okay? So we need to do a little bit of backtracking. The gravitational force between two charged objects is kq1, q2 over distance squared, right? Okay, everybody cool with that? And K is newtons meters squared over coulomb squared times coulomb squared divided by meters squared. Those cancel out. I get newtons. Hey, there's the force, right? This is old school. You've got this, right? No worries. Now, this is where this gets a little bit weird. Just a little bit. If you talk about OOI, it's a very similar equation, but you just divide by distance. And you're going, that's kind of weird. Why do you just divide by distance? Odd. Well, look what happens with the units. So I've still got newtons, meters squared over coulomb squared. I'm still multiplying by coulomb squared. So then I'm going to divide just by distance. Okay? So now I lose the coulomb squared. I lose one of my meters. So now I'm left with Newton meters. Newton meters is the same thing as joules. Okay? It's kind of weird. Now, here's the other thing that makes OOI different. All the other types of energies that we've talked about have always been positive values. MGH, 1/2 kx squared, 1/2 I omega squared. They're all been positive values. But here's what's different with OOI, okay? OOI is there the potential, no pun intended, for OOI to be a negative value.
Yes. Yeah.
Yes, if you have a oppositely charged particles. So if you have a positive charge and a negative charge divided by a distance, you're going to have negative OOI. If you have two negatives or two positives, you're going to have positive OOI. Okay? So this is an added twist. So if you look at what more and more, especially your generation, has defined your life, one of the key things that we have figured out is how to store electrical potential energy. So how does that impact your daily life? Batteries on your phones. If we didn't have the potential to store electrical, no pun intended, if we didn't have the potential or the capacity to store OOI, your phones would only work when they were charged, when they were plugged into the wall. Okay, that would be it. That's it. Phones are great. Guess what? They only work when they're, or you put a little hand crank on it. It's like, oh, you can start my phone, you know, these check messages, right? And that's how, that used to be how they would start cars. Okay, first generations of cars, we didn't have good batteries. So if you look at the old footage of cars, you were the battery. There was a crank that you would insert into the front of the engine, and you would crank that over, and that's how you would start the car. Okay, a lot of people got broken hands that way because it would start and then it would like start up and fly off. But thankfully we've got that. So we kind of need to go through some equations. So before I get into that, you all have been sitting, stand up, take a stretch, stop that for a second, and take a stretch and get into the equation.
It's going.
Now it's going?
It worked.
Okay. All right. So here's where gravitational potential energy and OOI kind of merge together. So let's say that I've got a parallel plate capacitor, easy to say, and we have a negatively charged plate down here, we have a positively charged plate up here. So if I were to take a proton and lift that up, okay? First off, why would I have to exert a force to lift that positive charge up?
Cause it's comfortable.
Yeah, it wants to stay here, right? Because it's close to the Chihuahuas and it doesn't want to go near the other St. Bernards. So it's just going to chill out down there. Kind of like this tennis ball. I had this tennis ball sitting here. That tennis ball just wants to hang out there, right? I mean, I could yell and go, jump, jump, okay? And it's not going to happen, right? It's like, this tennis ball's going to go, screw you. You know, I'm not going to do this. So if I want to lift this up, would I have to do work?
Yes.
Yes. I would have to exert a force over a distance to lift this thing up. Now, as soon as I let go of it, what's it going to do?
Go back down.
It's going to go back down, right? Because of the fact that it wants to return to that lowest possible energy state. So that's analogous to me lifting up a tennis ball. I do work and I lift up the tennis ball, right? I drop it, what's going to happen to that energy that I stored? It's going to change back into kinetic energy. Okay, right. I lift this up, I store a certain amount of potential energy, I let go of it, that proton's going to come crashing back down. Just like if I lift this up and let go of it, it's going to come crashing back down. So it's the same idea. Work is going to be done. I'd have to exert a force over a distance to store this amount of potential energy. Now, here's the confusing part about potential energy, is that it can equal a whole bunch of different things, okay? So if you look at what's on your sheet, so if you start with the idea, are you out?
Yeah.
Okay, I'll send you this video as well. So if you look at what's going to happen on this idea. So one option is that if you look at what Dewey is, you can express that as KQ1Q2 overall.
My bad.
Not R squared, you're just dividing by R, okay? So that works out to be Newton meters, otherwise known as joules. So the other way you can look at this is that it's Q times your voltage. So don't confuse potential energy with voltage, because here's the fundamental difference. So does anybody remember the units for voltage? Nope.
It would have to be.
Joules per coulomb. It's the amount of energy there is per unit of charge. So if you look at what happens here, this voltage is joules per coulomb. So if you multiply this delta V, which is joules per coulomb, times your charge, you're going to get units of joules. So part of it is just like the units game. Okay, how can we make this work out? So what this means, and let me point out one thing, okay? Notice that this is going to be change in voltage. So if you remember back to that electric field lab that you all did, so we need to take a quick diversion from this and go back to that electric field lab that you all did. And let's say that you had a positive charge. Why won't my pen write? Seriously? Hold on. Speaking of which. Okay, now it writes again. So you remember when you put that positive charge and then you plotted the lines that went around it? Does anybody remember what the sign was on those values? Were those positive voltages or negative voltages? Those are positive voltages, right? Now, this might be like 200 volts. This might be 100 volts. This might be like 50 volts, okay? So if you have a positive charge in the middle, Because the other way that you can express voltage, that is KQ over R. Okay, so when you go to calculate voltage, if you look at what happens with these units, so that's newtons meters squared over coulombs squared times coulombs divided by meters. You lose one of the meters, you lose one of the coulombs, so you get newton meters per coulomb, otherwise known as joules per coulomb. Okay, so there's the other way that you can look at voltage. So here's a visual, okay? So when you have a positive charge, as you get further and further and further out, these lines become small, okay? Your value of your voltages go from 200 to 100, whatever that is, okay? You get really, really close. So this is tough to visualize, but imagine this is looking down on top of a mountain, okay? And that positive charge is right here at the top of the peak. So imagine this is like a symmetrical mountain. So you have lines of like equal elevation as you go around. So you'd have a line very close to the top, let's say at a height of like 200 meters. And then you'd go down, then you'd have a line at 100 meters. And then you'd go further down and you'd have a line at 50 meters, right? And eventually you'd have a line at 0. So you can visualize this as being like a mountain. So here's this positive charge that's sitting up there on the top of the mountain, okay? And then you have a 200 volt line, and then you have like a 100 volt line, and then you'd have like a 0 volt line, okay? So instead of potential energy just being measured in joules, like you're gonna push a rock up here, and if you're just pushing a rock, oh, that's just gonna be measured in joules. But because of the fact that we're in effect like pushing a positive charge up here, if you're talking about voltage, is how much energy there is per unit of charge. So this is where voltage and energy kind of merge. So when you're talking about voltage, it's energy per coulomb. If you're just talking about energy, that's just joules, okay? So it's a subtle difference, but it's going to be important later on. So here's what I want you to see. Is that, let's say that I'm going to take a proton and I'm going to shoot it up the mountain. So I'm going to shoot it up the positive mountain, okay? So does that positive proton want to go near the positive charge that's at the top of the mountain? No. You shoot it up there, what's it going to do? Speed up or slow down?
Slow down.
It's going to slow down. So it's the same idea as rolling a ball up a hill. You roll a ball up the hill, what's that ball going to do? It's going to slow down, right? Okay? And you're going to store gravitational potential energy. So the same thing is happening here. If I shoot a proton or another positively charged object near another positively charged object, that doesn't work well because they don't want to be near each other. So it's going to start to slow down, and eventually what's it going to do? Stop. So it's like compressing a spring. Oh, it's going to stop. And then it's going to go what? Then it's going to go, oh, we're going to shoot this thing back in the opposite direction. So it's like rolling the ball up the hill. So when you have a positive charge value that you push towards another positive charge value, there's a couple of things you need to keep in mind. The voltages around the positive charge are going to be positive values that are going to decrease as you go further and further and further away. It's an inverse relationship. So if I'm going to do work, I'm going to push this thing up from a lower positive voltage up to a higher positive voltage because it doesn't want to go in this direction. So you got that visual. So if you look at the idea that UE plus kinetic energy is going to equal some constant. Now, I'm just going to make up some numbers to make this really simple, okay? So let's say we're going to calculate UE, and we're going to have KQ1 Q2 over R, because this is how we're going to calculate UE. So we're going to make this really simple. I'm going to make the top numbers up there have a value of 24. I don't care what the numbers are. We're just going to make the math easy. I'm just going to say that that's 24. Okay? So we're going to look at different values of radius. So we can have a radius of 2. So if I take 24 and divide that by 2, I'm going to get 12. So that's meters. So if I go to 1 meter, I'm going to have 24 joules, right? And if I go a half a meter, I'm going to have 48 joules. So if I were to draw a graph of UE versus radius, what would that graph look like? Cassidy? It's going to go up. Okay? Like up like this or like that? This one? Well, look.
It's gonna go, because the potential.
Let's plot these points. So here's 0.5, right? And that's 48.
So it's gonna go
1 meter was at,
like
2 was at
12.
12. Something like this. Okay, cool. So this UE versus radius graph is going to go something like this. Everybody cool with that? Because we're dividing by R. All right? So the closer I get, the more potential energy I'm going to store, right?
Of what?
Good with that. Now, we also know that UE plus kinetic energy, because energy has to be conserved, always has to equal constant value. Just like if I lift up this rock and I store 5 joules of potential energy, I let go of it, when it lands it's going to have 5 joules of kinetic energy. Halfway down it's going to be 2.5 and 2.5, right? It's the same idea. So here's my UE calculation. My radius gets smaller, I'm storing more and more potential energy. Now visualize this. Let's go back to the mountain idea. I'm going to shoot this positively charged particle. When I initially shoot that positively charged particle, is it going to have a lot of kinetic energy or a lot of potential energy?
Kinetic.
It's going to have a lot of kinetic energy, right? So then as it goes up, yes, how big?
Sorry.
Okay, I don't have my glasses on. You're going to have to do better than that.
Aren't you supposed to do this class?
It goes into these, they're like screws.
Oh,
Pardon the interruption.
stop that camera for a
Your
second.
students, if you
Are they
have
filled?
contact
Stand
with
it.
private
So let's make the math easy. Let's say this constant is, I don't know, 60. Okay, let's just say that's our energy constant. The sum of all the energies at any given instant has to be 60. Okay? So what's going to happen is that if you were to look at, come back here, UE kinetic constant. So that constant's going to stay the same. That's why we call it a constant. So when we had a radius of a half a meter, we had 48 joules of UE. So how much kinetic energy did we have then? 12 joules, right? Okay. When we were at 1 meter, we had 24 joules of potential, which means that we had joules of kinetic. And we were at 2 meters away, we had 12 joules of ooey, so we had
48.
48 joules of kinetic. Okay, so now let's look at basically what we're saying. Here's this positively charged particle. We're going to shoot this other positively charged particle at some distance away. When we were at 2 meters away, we had a certain amount of ooey, which was 12 joules, but we had a lot of kinetic energy, right? Okay? So when we're 2 meters away, we have a lot of kinetic energy, but we don't have much ooey. So as this positively charged particle approaches this other positively charged particle, what's going to happen to the amount of ooey? Increase or decrease? Increase. So as it gets closer, I'm increasing my ooey. Okay? Well, where's that energy coming from? The kinetic energy. So I'm sacrificing kinetic energy. So here's this ball, it's positively charged. Here's another positively charged particle. I shoot this towards it, it's going to start with a lot of kinetic energy. But as it approaches, what's it going to do?
Slow.
It's going to slow down, and eventually what's it going to do?
Step.
Stop, and then
Reverse.
Back up.
it's going to go back up. So in this regard, this makes sense. Okay, this is the easy side of the ooey variable. Okay, cool, right? So I shoot it towards it, or the other way that you can look at it is that if I want to get these two particles together, I have to do work because they're two positively charged particles. These things don't want to be near each other. So if I'm going to do work, I'm going to push them together. So if you think back to like that balloon lab that you all did, okay? You had these balloons that don't want to be near each other because they were positive, they both had a negative charge. And if you wanted to push them together, you had to do work, right? And when you could push them together, but as soon as you let go of them, what's going to happen? Or bounce back, because Mother Nature doesn't like that. So this one, everybody's cool with. Got it. Good. Okay? Here's the problem, though. Here's the problem. Let's say that I'm going to have a negatively charged particle that I'm going to shoot towards a positively charged particle. I want to look at 2 meters, and we're going to look at what's going to happen at 1 meter, and we're going to look at what's going to happen with a half meter. Now, here's the struggle that I have as a teacher, is to kind of get you to see through this. But this is where we're going to develop the same mathematical model. So we're going to look at ooey, kinetic, and a constant. Okay? So let's say that constant is still 60 joules. So let's stick with the numbers that we already have. All right? Now, when I go to calculate ooey, it's going to be KQ1, Q2 over R. Now I have oppositely charged particles. So what's going to happen to the sign of my value of ooey? Now it's going to be negative. But you said, oh, Mr. Workham, we've never talked about negative energy before. Well, when you have charged particles, you can have negative ooey because of the fact that if you look at how that's calculated, you have K, it's constant, but now you can have oppositely charged particles. You can have a positive and a negative. Now, having oppositely charged particles, because we're multiplying those together, that can generate a negative ooey value. Okay, so if you look at the numbers, they're going to be the exact same. They're going to be 48, 24, and 12. But those are going to be negative values. Okay? That's kind of weird. Now, but everything still has to add up to 60. So what's going to be the value of my kinetic energy when that OOI has a value of negative 48? Everything still has to add up to 60.
72.
What are you going to have? 108? Right? Because if I take 108 plus negative 48, I get. So what's going to be the value of my kinetic energy here? 84. And then it's going to be 72, right? So here's what I want you to see. When I had two positively charged particles and they got closer, what happened to my kinetic energy? Went from 12 to 36 to 48. The kinetic energy became bigger, right? So if you look at this trend, what's happened to your kinetic energy? It's becoming smaller, okay? But here's the idea. Everything still has to add up to a constant, right? So if you look, on this OOI, this is when you were like a half meter away, and this is when you were 2 meters away. So when you were a long way away, you didn't have much potential energy, but you had a lot of kinetic energy. So as you got closer, the amount of potential energy became bigger, but you lost it as kinetic. So over here, this is 2 meters away, this is a half meter away. Why is this thing, if you look at what's happening here, right? So you're going from a half meter away, you're going to 2 meters away. Why is it speeding up? Because they're attractive. So now I've got a negative, now imagine this is negatively charged, and imagine this is positively charged. As they get closer, it's actually going to speed up. But it's the exact same idea, okay? It is the exact same idea. Let's just stop there because your minds need a break, okay? So we will take this up tomorrow. So, and if you kind of get this idea, you've got almost all of potential energy being. Evan?
But at 2 meters, they're at 108 joules. Then at half a meter, they're at 72 joules of kinetic energy.
Right?
No.
So doesn't that mean it's slowing down?
You put them.
Oh, I flipped those.
Oh, okay.
So it's
Yeah.
half a meter on the top.
Yeah, that's a half meter, and then that goes down to 2 meters.
Okay, that's,
Yeah.
that's better.
I flipped that, yeah. Okay, so stop that. We'll finish this up tomorrow.